Hello, everyone. I'm Jiajun Wu. I'm very honored to have received the Samsung AI Research of the Year award. I'm a new assistant professor at Stanford University who have just started in July this year. And excited to be here and to talk about my research. My research is, the title of the talk is Learning to See the Physical World. So humans live in the physical world. As humans, we effortlessly see the world, navigate in the world, and interact with the objects in the physical world. So as AI researchers, we want to build AI and machines that can replicate such abilities. So to do that, let's first look at what humans can do. But in the case of a very simple game, the popular game, that is the game of Jenga. And this is a 6-month-old baby playing the game of Jenga. Looking at what the baby is doing, she's able to play the game in a different way. Although not playing the game the way that we expect, you can see from this video that this 6-month-old baby has an amazing ability to recognize what's in the scene, to pick up objects, segment the objects, find the blocks, pick up the blocks, interact with it. And this is the theme of my research. And so that's why I sometimes call it the infant machine. That is, can we build a machine that learn and behave like an infant for any new objects, including objects we've seen like blocks, but for a young child, and we have never seen objects like this. So for any new objects, including those we have never seen before, can we recognize its shape, geometry, and physics, predicting how it will behave if we interact with it, and to actually interact with it? So this is the theme of my research. So how to do that? Well, of course, we can try to use now this very popular deep networks, and you can see, in scenes like this, the networks does really well in segmenting objects like cars and roads. On the other hand, such kind of approach, if we directly try to scale it up to not only recognize objects like cars, but also to unseen objects, to object geometry, to object physics, then we have a challenge, because by relying on data, how can we really scale it up to collect annotations that are beyond object semantics like cars? Now, if we want to annotate the geometry of the object, if we want to annotate the physical properties of the object, that just seems very hard, and it's almost impossible to collect such annotations to train the deep networks. So an alternative approach is we can try to think about, we're living in this physical world, then there's physics governing us, and so what's the physical model behind it? For an image like this with a few blocks, we understand that there is underlying physical states, which includes object geometry, physics, intrinsics, there are extrinsics like positions, and scene descriptors like lighting and camera parameters. And our goal here is, how can we really turn these states like object intrinsics and extrinsics into images? And this is the physical model behind what we see. And it's an important subject in computer graphics called rendering. Beyond a single frame, you can do that for multiple frames. Across the frames, there is dynamics for it. Condition on the current state, condition on actions, and what's going to happen in the future. In a video like this, the actions you can see is, you can assume it's like gravity. Right, so this kind of modeling approach is trying to understand what's the physical model behind the physical world, and to use it for us to understand the scenes, for scene understanding. But such a model also has other challenges. For example, the biggest challenge is probably once we have this top-down model. Now, when we understand object geometry and physics, we can imagine how the scene will look like. But if we want to solve a bottom-up inference problem, if we're not given the scenes, how can we really infer the geometries? Right? This is an unsolved problem, and traditional approaches like sampling, MCMC, are just they're too slow to be practically useful. And second, models are always approximate, so they're not good enough to capture every details of the world. So the theme of my research, or the philosophy behind my research, is to integrate the two, to combine learning with modeling, so that you get the power of both the data and the model. And concretely, we have two themes of research. One is learning to invert. That is, as we said, how can we really use top-down models for bottom-up inference? And our solution is to learning to use it, to learn to invert the physical model, but take the intermediate representations, or take the targets from the physical model as our training target, as our intermediate representations of training. The other is learning to augment. As we said, models are only approximate, not capturing the details in the world, maybe too deterministic. So can we use learning to augment it to make it more accurate, more efficient, to able to handle uncertainties? So putting them together, the key principles behind my research is to build physical models for these physical worlds, and to think about what the model doesn't give us and see if we can use learning to help us to solve it. So now let's look at some concrete examples about how learning can be integrated with physical models. Here is an example where we look at a simple task. If we are given an image, a 2D image with only a single object, can we infer the 3D geometry, right, of that, seeing object shape? So if we want to learn to invert a physical model, let's first look at what's the physical model in this case. Here we have a 3D shape, and again, this is a very simplified setting. You have a 3D shape, and let's think about how the image is formed given that 3D shape. So you put that 3D shape in a 3D space, and there's a light source. And the light source sends out rays to the object. It hits the visible surface of the object. They get reflected into the camera. In front of the camera, there's an image plane. And this is, from the image plane, you actually see the object. So we're essentially seeing about the object geometry is actually the visible surface. But in this case, you only see the 3 legs of the chair. You're not seeing the 4th leg because it's occluded. And we know that the chair has 4 legs because we have a prior knowledge. The chairs must be stable, so it must have 4 legs. But all you can see from the image is the visible surface, which shows chairs has a back, has a bottom, but only has 3 legs. And we're using our prior knowledge to imagine the 3D geometry. So accordingly, if we want to invert this physical model, maybe we can design a system, but also, for shape estimation in 2 steps. The first step is to do depth estimation. That is, we go from a color image, but to estimate the depth of the object. For a depth map, you can see it as a reparameterization of the visible surface. Every pixel on the depth map corresponds to a point on the surface. And second, you're doing shape completion. You're going from this visible surface or the partial surface to complete the shape. But for this part, the image is no longer being helpful because there's no more information you can get from the image about object geometry. And all you can do is to use your prior knowledge, use machine learning to help you to complete the shapes. Because you have seen many chairs, they're all stable, they all have 4 legs. So you learn this knowledge, the chairs must be stable, and use that knowledge to complete the shape. So in this case, you can see the depth map or visible surface is important intermediate representation that we take from the physical model. And condition on the depth map, the input RGB image and output 3D shape actually becomes conditional. So following this philosophy, we designed a system that has 2 steps. Both are neural networks, but the first neural network estimates the depth from the color image, and the second neural network compute the shape, output the 3D shape geometry from the depth. And compared with the end-to-end approach that only has a single neural network that outputs shape directly from the image, if we test it on images like this, which you can see is a kind of a pretty actually challenging and useful chair, direct output without modeling depth, this is what you get. But by modeling depth, you can see the output just becomes much more accurate and really enforces the system to care more about object surfaces, which is really what matters to our perception of the reconstruction time. And here's another example where you can see that the geometry is also being much better by modeling depth. Okay, so this is like one simple idea of how the intermediate representations can help us do better in reconstruction. But as we said before, we want to generalize to new objects you've never seen before. How would such a system generalize? If we try to train it on object classes like chairs, planes, and cars, and then we test it on the table, and this is what you get. You send it to a network, and this is the output of the system. Does it look like a table? Well, I would say it looks much more like an airplane. It does a little bit look like a table because it shares the top of the table, right? But why is this happening? Because when the system is given a table, it's like, I've never seen this before. I don't know what that is. But the top of the table does look like it's round, does look like some of the airplanes I've seen. It's thin and round. So why don't I just try to retrieve an airplane? Essentially, the system hasn't learned what shape computation means. Instead, it's just trying to retrieve smart shape from the treatment set, the nearest data. This is not only a problem for our approach, but it has been a common problem for the general literature. There are a lot of work in this direction, and they all suffer from this problem. So how to build a system that generalizes to even objects from unseen object categories? Again, we're going back to the idea of looking into the physical model and seeing how we may use learning to invert the physical model. If we look a little deeper into the second part of the system, projecting depth, we're here projecting a 2D depth map back into a 3D, as we said before, visible surface. So essentially, you're still doing this 2D depth map to 3D visible surface back projection. And this is a deterministic and fully differentiable process. And if this is differentiable, deterministic, and something that we can write it down as mathematical equations, why would we have this shape completion network, the second stage of the system, to be over-parameterized and to relearning this thing while we already completely has understood it and can write it down. And it's so universal that every image is the result of a projection model. So it's universal rules that we already know about. So our solution is, instead of having the system to be over-parameterized and relearning back projection from 2D to 3D, what if we just build it into the system? So now the system first estimates the depth and then back project it into a partial surface, as you can see here. Now the surface in 3D, but it's partial. It only has 3 legs. And then the second part of the system, shape estimation or shape completion, now can really focus on completing the shape using my prior knowledge that chairs have 4 legs to complete the shape instead of relearning this back projection. So with this simple change, now if we take the models training on chairs, planes, and cars, and we test it on this table, this is what you get before, direct prediction. This is what you get by having depth and projection as intermediate representation. Right now you can see the results are much better, and it really matches the input. That it looks much more like a table. Remember, again, this system has never seen a table; it has only seen chairs, planes, and cars. And this is our model called generalizable reconstruction that published, I think 1.5 years ago at New Rips, with leading authors Xiuming and Zhou Tong, my collaborators, PhD students at MIT. Okay, so we've seen how the system generalizes to tables, but now let's try on even more object classes, bookshelves and sofas. Again, the system was only trained on chairs, planes, and cars. It has only seen chairs, planes, and cars, but now you can see how it performs on bookshelves and sofas. On the right, there are some baselines, which you can see they're doing okay, but not perfect. It's, trying hard to approximate the bookshelf and the sofa. And this is the output of our system, Run. Still, a lot of artifacts, a lot of places that we can improve, but it does approximate the input shape much better without seeing any bookshelves and sofas. And you can compare them with the ground truth as well. And here we try something that's even crazier. What if we just test it on non-rigid objects like human bodies and horses, while the system has only seen chairs, planes, and cars? And this is what you get. Comparing them with the ground truth, although you can still see all the bumpiness and imperfections, but to me it's quite impressive that the system are able to learn that surfaces must be complete and shapes must be complete to reconstruct objects like humans and horses with only seeing chairs, planes, and cars. Okay, so now we have shown important representations in computer graphics, especially 2.5D surfaces, like the depth map, visible surfaces, can serve as intermediate representations together with projection to help us build a learning system that is much more generalizable and also performing better. This is learning to invert. So on the other hand, we also want to see how this 2.5D surfaces can be used for intermediate representations for augmentation. What does that mean? If we have a traditional graphics engine, given a shape, texture, I can render a picture. But what if I want to generate objects that I've never seen before, or paint it with textures I've never seen before? So here we use a generative neural network called generative adversarial network to synthesizing novel 3D shapes. And this is kind of a pretty common or popular technique, generative adversarial networks. But what's important here is now we can still do projection, but we do it in the other direction. We do a forward projection. We take the generated 3D shape and project it into 2.5D surface. That is depth map, as we said before. And we can apply a 2D texture network. Then we just paint the textures directly on the 2D image by translating the depth into an output, a color RGB image. This allows us to not only generate 3D shapes inside the novel objects, shapes, but also generate 2D pictures of these objects with corresponding textures. Such a disentangled representation also allows you to, for example, synthesizing 3D shapes, and then take textures from images that I look at, that I really like. I'm like, oh, these pictures has very nice cars, but how will the textures of these cars look like if I apply them on the shapes of other cars I just synthesized? And this is what you can get. By having this kind of a hybrid or augmented graphics engine, now you're augmenting the physical model, projection, depth, with your learning system to synthesizing new shapes, or also to synthesizing new textures. So this is the power of learning to augment a graphics engine. And of course, we can put them together by, given a scene of multiple objects, we can first try to invert it using a slightly, updated version of our system that I presented earlier. But to first invert it, recognizing object geometry, recognizing their pose and texture. And then I'll be like, now I have this semi-interpretable representations and objects, cars are at the center. What if, how the scene will look like if I move the object to the right? I can directly edit these representations and then put the edited representation back into my augmented physical model, the graphics engine, and to re-render how the scene will look like with everything else stay the same, with the only exception that the objects, the position of the objects have been changed, and now the cars are on the right. Okay, so this is the power of integrating learning to invert a physical model graphics engine and to augment a physical model of graphics engine. And this is what we can do in image understanding and in scene understanding and scene manipulation. And the world is not only static, right? We also understand, like in this tower, it seems like the blocks are going to fall. So how to capture dynamics? And the most straightforward idea is probably just to do inverting graphics engines and take the output of the graphics engine directly send it into a dynamic system, predicting you simulate what's going to happen in physical simulation and re-render what's going to happen in the future. Turns out this kind of simple idea could be actually very helpful. Given an image like this, I can reconstruct inferring object geometry, texture positions, reconstruct the scene, and predict what's going to happen if there's a wind coming from the right, or if I push the object. Or if I'm seeing a tower of blocks that are already falling, I can also plan accordingly. Right? What's the stabilizing force I can put to stop object tower from falling? And we also even tried to deploy on a real robot. So given a scene like this, if I want to reproduce or rebuild this bridge or a tower, what do I need to know? I have to understand there are multiple objects, 7 blocks. They have different sizes. They have different colors. I have to understand there is physics. So if I want to rebuild a tower, I have to start from the bottom. So we actually tried and deployed our system on a real robot, and the robot is actually able to recreate a tower or bridge like this. And here are more examples, like 10 different trials. And as you can see, the system is not 100% accurate, because especially going from a single image, right? Everything here is from single image. Estimated depth, the distance of the blocks is challenged. But you can see in most cases, 7 of the 10 cases, the robot was able to recreate a tower or bridge from just a single image. Okay, we said we want to use learning to help dynamics models. Before we said learning can be used to invert and augment a graphics engine. And for dynamics models, the idea is the same. If we just directly applying a dynamics model, then there are a lot of things that are missing. For example, if I'm showing you 2 objects here, and they look almost identical, but if I put them into the same external force, like there's an external object hitting it, the outcomes are very different. Why is that? This is because the top object is made of aluminum, which is much lighter than the bottom object, where the top block is made of steel, which is much heavier. So physical properties really affect your dynamics models. And you probably want to use learning to invert your dynamics models to not only understand object geometry, but also understand their physical properties. Also, if I'm giving an object like this and I try to push it multiple times, even if my force is from the same direction, and my force identical, and the magnitude and direction is identical, then you can see that the outcomes are stochastic. Right? This is because the world, there are all those details which are really hard to model, microsurface, microfriction, and these will all lead to changes in the outcome of dynamics. So in practice, it's really a stochastic process. But any physics engine or any dynamics model you use off the shelf is usually deterministic. This shows you'll probably also want to use learning, not only to invert dynamics model to estimate physical properties, but also to augment the dynamic model to make them stochastic. Due to time constraint, I won't talk in detail about any of these papers, but I'm happy to share with you afterwards offline. Learning also can help us to learn dynamics models, applying them on scenes that we cannot typically do. Here is an example where we try to learn a dynamics model not only between rigid objects, actually between collection of particles using a hierarchical dynamics, graph networks. And by doing that, you'll see that the learned system can actually not only simulate how rigid objects interacting with each other, but also how fluid they interact with rigid objects. This is another aspect where learning can be used to augment the dynamics model. Okay, to summarize, so my research is about using learning to invert, if I don't know how to use the top-down models for bottom-up inference, I can use learning to invert these physical models for efficient inference. I can use learning to augment approximate dynamics models or graphics engines to make them better, more efficient, and able to handle uncertainty. And to summarize, again, we really want to think about what's the physical model behind the physical world if we want to deploy or build AI system for the physical world. We also have to be very careful here, because from history, we have learned decades ago that if you're building things that are too much, that are too restrictive, that are not universal, it really eventually hurts your system's ability in generalizing in the real world. But here, what we are trying to build is really the minimal structure, but also the most universal structure, right? Projection. Every image you're seeing in 2D is an outcome of a projection from 3D structure. So building that in doesn't really help you, but it doesn't really hurt you. But the universal structure really allows or help your system to generalize much better. So this is what we want to think about. What's the minimal physical structure for the physical world, and to build them into a learning system and use your learning system to learn whatever the model doesn't do. Thank you very much.